Welcome to the Explainer. Today, we are tackling a huge topic in biotechnology, enzyme immobilization. Look, if you're gearing up for an exam, this is for you. We're going to break down exactly how this amazing technique makes everything from your food to your medicine way more efficient and a whole lot cheaper. So let's start with a big question. Enzymes, right? They're nature's little miracle workers, speeding up reactions like nothing else. But here's the problem. In their natural state, they're super fragile. It's like trying to build something with tools made of smoke. They're unstable, you only get to use them once, and they can be really expensive. So how do you fix that? Well, the answer is this really clever technique called immobilization. All right, here's the game plan for today. First up, we'll cover the basics, the what and why. Then we'll get into the how, looking at the two main approaches, physical and chemical methods. And finally, we'll connect all the dots and see the massive impact this has on the world around us. Okay, let's dive right in. Before we get into all the cool methods, we've got to get a solid handle on what we're actually talking about, and maybe more importantly, why on earth we even bother doing it. So, what is it? At its core, the idea is actually pretty simple. You take a free-floating enzyme and you lock it down. You anchor it to something solid or trap it inside a structure. The enzyme can't wander off, but, and this is the crucial part, its active site is still free to do its job. It's all about turning a fragile, one-time use catalyst into a tough, reusable workhorse. And this is where you really see the difference it makes. It's a total upgrade. A free enzyme is like a disposable tool that gets lost in the mix after you use it once. But an immobilized enzyme, that becomes a permanent, reliable part of your toolkit that you can just use again and again and again. And that leads to some massive industrial advantages. You can reuse them, so you need less enzyme to begin with. They often become tougher, able to handle more heat or changes in pH, and critically, because the enzyme is stuck in place, your final product is totally pure. You just filter it off. And all of this adds up to one thing. It makes the whole process way, way cheaper. Okay, let's get into our first set of techniques. How do we actually do this? Well, physical methods are all about holding the enzyme in place using physical forces or barriers without creating any new, permanent chemical bonds. So the simplest way is a method called adsorption. Honestly, the best way to think about this is like molecular static cling. We're just using weak forces to get the enzyme to stick to the surface of some support material, like porous carbon or a special kind of clay. You pretty much just mix them together and they stick. Now, the big pro here, it's super simple and cheap. And because the forces are weak, it's very gentle on the enzyme. But there's a trade-off. Those weak bonds can break. If you change the temperature or the pH just a little bit, the enzyme can just detach and float away. That's a process called desorption, and it's a major downside. All right, so with entrapment, we're not sticking the enzyme to a surface. We're literally building a tiny cage around it. The enzyme is physically trapped inside the pores of a gel or within a tiny capsule. The holes in the cage are too small for the big enzyme to escape, but they're big enough for the small substrate and product molecules to move in and out freely. You know, a classic way to do this in the lab is by making calcium alginate beads. It's actually pretty cool. You mix your enzyme with sodium alginate solution, then you just drip that mixture into a bath of calcium chloride. The moment the drops hit the solution, they instantly turn into little jelly-like beads, with your enzyme safely trapped inside. It's a really common and effective technique. Okay, let's switch gears and talk about the more heavy-duty chemical methods. With these, we're not just relying on weak forces. We are creating strong, irreversible chemical bonds to lock that enzyme in place for good. Covalent bonding is really the gold standard if you want to make absolutely sure the enzyme isn't going anywhere. This method creates a powerful, stable chemical link, a covalent bond, between the enzyme and the support material. It's a permanent attachment. So, you can probably see the trade-off coming, right? The good news is you get this incredibly strong bond. No worries at all about enzyme leakage. But the bad news? The chemical reactions you need to create that bond can be harsh. Sometimes they can accidentally mess up the enzyme's delicate 3D shape, potentially damaging the active site and making it less effective. Now, our last method, cross-linking, is a little different because you often don't even need a support material. What you do here is use a chemical agent to create covalent bonds between the enzyme molecules themselves. You're basically gluing them all together into one big insoluble clump, or aggregate. And here we go. This table is your perfect exam revision tool. It lays everything out so you can see the trade-offs at a glance. Adsorption is gentle and reversible, but weak. Entrapment is also gentle, but it's irreversible. Covalent bonding, super strong, but carries the highest risk to the enzyme's activity. And cross-linking is a strong, irreversible method that sits somewhere in the middle in terms of risk. Okay, so we've covered the what, why, and how. Now for the really cool part. Where does this technology actually show up? Because trust me, this isn't just theory in a textbook. It's a game-changing technology that impacts the products you use every single day. Ever had a can of soda? Then you've experienced this firsthand. The high fructose corn syrup in it is made using an immobilized enzyme. That one application literally created a multi-billion-dollar industry. What about lactose-free milk? Yep, that's immobilized lactase doing the work. This tech is also crucial for making certain antibiotics, for making our juice and wine clear, and even in making cheese. It's everywhere, working silently behind the scenes. And the applications get even more futuristic, especially in healthcare. That little test strip in a blood glucose monitor, it's coated with an immobilized enzyme that reacts with the sugar in a drop of blood. They're also key in advanced medical tests and are even being used to develop things like artificial organs that can help manage metabolic diseases right inside the body. So, if you remember just one thing from all of this, let it be this. Immobilization is the technique that unlocks the true power of enzymes. It takes them from being delicate, one-shot wonders and turns them into tough, reliable, cost-effective tools for industry. Think about it. We've seen their impact on food, medicine, and diagnostics. So what's next? As we look at huge global challenges like creating sustainable energy, reducing plastic waste, or cleaning up pollution, you can bet that these powerful anchored biocatalysts are going to be a huge part of the solution. We are really just getting started.